Hello, everyone, and welcome to Chapter 4. This video will be discussing probability and counting, so a rather important set of sections as we begin our transition from the descriptive statistics in this class to the inferential side of statistics. So there are some things that we need to pick up along the way, and Chapter 4's probability and counting provides us with some of those important skills that we're going to be using throughout. So this video will be a bit long. We are covering a lot of ground across 4 different sections in our course. So section 4.1, 4.2, 4.3, and 4.4, each covering a different aspect of probability. We will be looking at some definitions, rules, and formulas, as well as some worked examples. And I would encourage you to use the video's bookmarks to your advantage when you're watching this, because again, it will be a longer video. And if you need to, play it on the 1.5 times speed. I might sound a little funny in doing that, but at least you'll get through the stuff a little bit quicker in that respect. All of the problems and things that this video will be demonstrating to you and we're working through do come from our textbook, Hawks, and so there was copyright information on the first page here. So just citing my sources for where all the information will be coming from. A few important notes before we fully dive into this. First of all, you're going to have to know how a deck of cards is organized. There is a separate video on this in the YouTube channel, as well as posted in our LMS Canvas, okay? So do make sure you take a look at how a deck of cards is organized if you are not familiar. You will need to know that for the purposes of exams and the final. Also, remember that probabilities can be expressed in one of 3 ways, as a decimal, a fraction, or a percentage. And you do want to make sure that you always simplify your fractions, okay? So you get to choose one of those 3 presentations for how you want to express your answer if it's dealing with probability. Sometimes it's easier to just leave it as a fraction. Sometimes it's easier to convert to a decimal or leave as a decimal, depending. And you'll see that demonstrated throughout. And do make sure with regards to the online homework, any hand-in assignments, exams, the final, etc., you do follow directions with regard to rounding if there are directions on that. Okay, so very important that you read those thoroughly. Okay, we are ready for section 4.1, which deals with the basics of probability. So there's a lot of vocabulary that we're going to be looking at here. So you should be able to, at the end of this section, be able to define these terms, okay, related to basic probability. You should be able to do some things, such as creating a sample space, using different strategies for doing that, whether it be a list, a table, a tree diagram, etc., and be able to find experimental and classical probabilities. So we have a list of definitions here. You will need to know these definitions because you're going to see the vocabulary come up quite a bit. So we have here an experiment or trial. This is any process with a result determined by chance. So experiments can be things like choosing a random card from a standard deck of cards, flipping a fair coin, rolling a fair 6-sided die, rolling a fair 20-sided die, etc. An outcome is each individual result that is possible for an experiment. So if we flip a coin, the outcomes we could have are heads and tails. We also have something known as a sample space. This is the set of all possible outcomes for a given probability experiment. So if I said to you, we're going to roll a fair 6-sided die, the sample space would be all the possible outcomes, the digits 1, 2, 3, 4, 5, and 6. Flipping a fair coin would be heads and tails. An event is a subset of outcomes from the sample space. So we get a little bit more specific. So for example, if I said rolling that 6-sided die and I'm interested in the odd numbers, then that is the event I'm describing, rolling an odd number. Those outcomes would be 1, 3, and 5. Similarly, if I'm flipping a fair coin and I'm really interested in getting heads as an event, then the only outcome in that particular event would be heads. Okay, so let's see if we can make some sense of this. So I think I've kind of overviewed this one already, but let's consider rolling a 6-sided die, and we're interested in the values of the die that are even. So what exactly is the experiment here? Well, the experiment is actually rolling the 6-sided die. Okay, that's the action that we are performing. The sample space is S is equal to 1, 2, 3, 4, 5, 6. You'll notice that we use the sample space, the variable S, capital S, and we use this set notation, so the fancy brackets. to express all of the outcomes. The event E, we generally use capital letters to symbolize or represent the events. And in this case, it's the values that are rolled that are even. And so the outcomes in the event then is the set of outcomes 2, 4, and 6. So again, using some of that vocabulary. Now, one of the things you need to be able to do is to generate the sample space. Remember, sample spaces are the list of all the outcomes, and doing this can be easy and straightforward, or it can be a bit tedious, depending on how complicated the experiment is, what we're actually doing. So we do have some strategies here. We could use a tree diagram, we can use a chart, we can look for patterns to help us, or a comprehensive or exhaustive list where we just sort of power through and generate the sample space. So let's write the sample space for the following experiment. So part A says flipping a fair coin and then rolling a 6-sided die. So you're doing sort of two things, right? We're flipping a coin and rolling a 6-sided die. So I think it's easy enough that we can just use a list, just power through this if we think through it logically. So we flip a coin. So the coin either has a head or a tail, okay? And then we roll the die, and the die has the outcomes 1, 2, 3, 4, 5, and 6. So one potential outcome could be that I flip heads and I roll a 4. So H4 could represent an outcome, okay? Similarly, I could flip tails and I could roll a 3. So T3, tails and a 3 could be another outcome. So systematically, it makes sense then to maybe list these in a particular order, which is what I chose to do. So if we consider the coin toss being tails, then what are all the possible outcomes that we can have with the die? Well, that would be T1, T2, T3, etc. And similarly for flipping heads, right? I could have each of the 6 digits on the die come up for each roll, or each flip rather, of the coin. So 12 total outcomes here, and you have the sample space. So again, this might be an easier one that we can just simply list out by thinking through this a bit logically. This isn't the only way to approach the sample space for this problem. Some folks who are watching might think, well, could we use a tree diagram for this? And absolutely, that would be okay to do. Okay, now let's continue this and write the sample space for the following experiments. We want to flip a fair coin 3 times, so 3 times in a row. So if I were to do this, I flip the coin, I could get tails on the first roll, I could get tails on the second toss, and maybe heads on the third toss. So TTH could be one possible outcome, okay? So how then do we capture all of them? Now, this might be a little harder for people to sort of try to list out explicitly. Not impossible. If you're good with making lists and you enjoy that kind of thing, you can do it. I chose to use a tree diagram. And so what we do is we consider the first toss, and I hope we all agree that there are only 2 options, right? Heads or tails on the first toss. Now, from each one of those, we also have on the second toss a head or a tail. So for example, if we follow this, the first toss could be heads, the second toss could be tails, okay? So you're kind of following the paths on this particular diagram. Similarly, if we selected tails as the first toss and heads as the second toss, okay, that would be a particular outcome, a T and an H, tails, heads. And if we add the third toss, obviously this begins to branch out, looking a bit more like a tree. Now we have sort of 3 paths that we have to follow. So people wonder, well, then how do we figure out what the outcomes are? Well, you have to travel along each of the paths. So if the first toss was a heads and the second toss was a heads, then the third toss could be a head or a tail. So in this case, I chose HHH to be the first outcome, and that's literally what the first outcome would be. The second outcome would be the next one, HHT. Okay, so you're traveling, the first toss is heads, second toss is heads, third toss is tails, and then the next one would be heads, tails, heads, etc., thereby listing all of the outcomes. Okay, so they're a string of 3 letters or 3 values from the coin. So this is one way in which we can examine sample spaces using a tree diagram. Okay, now if we consider another example, we have a family that has 3 children, and we want to find the sample space for the gender of each child in regards to birth order. So gender here we're considering as boy or girl. Um, this sounds somewhat similar to the previous example, especially with there only being two options of boy or girl. So we could replace the heads for boys, H for B, and replace the T with a G for girl, and you'd essentially have the same tree diagram, only different variables, obviously, and the sample space. So interesting that we've got that sort of relationship here. So that is, again, how you can accomplish this problem is use the same tree diagram as the previous slide, but just simply replace the H with B and T with G, or vice versa, if you're so inclined, and the sample space will be the same in that respect. Okay, we want to roll two six-sided die, and we want to add the results. Okay, so this one is a bit more complicated. So this means if I roll a 3 and a 5, what I need to do is I need to sum those digits, sum those results. So this would be a sum of 8. Okay, so if I roll a 6 and a 3, that means I would have a sum of 9. So how do I keep track of all this? Well, one way is we can use a chart, because there's a lot going on with respect to rolling the die. So we label each side of the chart, die 1 and die 2. There are the digits for the first die, there are the digits for the second die. And so then what we need to do is fill this in. So the red numbers are representing the sums. So for example, if I rolled a 3 and a 5, you'll notice that that comes up in two locations. So die 1 could be a 5, die 2 could be a 3, and that would give me a sum of 8. And similarly, die 1 could be a 3, and die 2 could be a 5, and we get a sum of 8. And there are other possibilities here. So people might wonder, does the order in which we roll the die matter? In other words, I'm saying rolling a 3 and a 5 is 3 indicative of die 1. Because I'm writing it in that order, one could understand this to be that the 3 is coming from die 1 and the 5 from die 2, unless I specified otherwise. Okay, so other examples here. So for example, die 2 could be rolling a 6, and I don't know, die 1 could be a 5, and so that would be a sum of 11. If you study this chart, there are all sorts of interesting patterns on here, and we'll actually return to this chart in a little while, but this would be considered the sample space, okay? And you could more explicitly write what the sums are, and that would be the digits from 2 to 12, since those are the sums that are represented here. Okay, but using a chart is an easy way to keep track of all the possible outcomes in the sample space. Similarly, if we had asked you to roll two six-sided die and multiply the results or subtract the results, the chart would also be very much so a helpful thing. All right, we're ready to move on now to the different types of probabilities, and we have three different methods we use to compute or calculate the probability. The first is known as a subjective probability. This one's interesting. This is sort of your educated guess on the chances that something will occur. Okay, so this would be like you saying, I think I am going to pass my statistics class, and I think there's a, I don't know, 75% chance that I'm going to do that. Okay, that's a subjective probability. This, of course, is the least precise of the probability types. It should be obvious as to why, because it's our educated guess, and sometimes those educated guesses are somewhat biased. It could be something like having overconfidence or maybe not enough confidence in oneself. So, for example, somebody saying, yeah, I'm probably going to fail this exam, right? Well, they may be underestimating their abilities in that respect. So that's why this one is a little bit more least of the precise probability types. We also have experimental or empirical probabilities. This is where we have an event E, and we use the notation P of E. This is read as the probability that E occurs. This is equal to F over N, where F is the frequency of an event, E, and N is the total number of times the experiment is performed. So this involves sort of repeating the experiment over and over again, such as flipping a fair coin. Okay, so if somebody says to you, I'm going to flip a fair coin 100 times, and I am going to count the number of times that tails comes up, they're referring to this experimental probability. Okay. Now that's different than the classical or theoretical probability. And this is where we have instead that the probability that E occurs, this is equal to the number of outcomes in the event, N of E, over the total number of outcomes in the sample space, N of S. This is generally the one that everyone is used to. So the easiest example would be a coin toss. Okay, how many outcomes are there in the sample space? There should be two, heads and tails. So that is our denominator. That's our N of S. And I'm interested in flipping a tail, okay, getting tails. So that would be the event. So how many times does that occur? How many outcomes are in that sample space? The answer is one. So the probability of selecting tails would be 1 out of 2 or 1/2 or 0.5. So that's the classical or theoretical probability. Again, the one we're most familiar with. Okay, so let's look at some examples here. So suppose I ask you and your classmates to flip a coin 100 times and record how many instances the tails come up. I take everybody's results and I combine them. The result is a fraction, and what we'll notice is that it is actually pretty close to 1/2. And again, this is known as experimental probability because we're doing this experiment repeatedly, right? Just constantly keep doing this and counting the number of times tails come up. Now, we do know that the probability of flipping tails is exactly 1/2, as we talked about a few moments ago. So that again is known as the classical probability, okay, the one that most people are familiar with. Now, in this instance of sort of repeating this experiment, flipping that coin over and over again many, many times and counting the number of tails, what we're noticing is that that experimental probability, that fraction that's getting close to 1/2, is getting close to the classical probability. That's a phenomenon known as the law of large numbers. It's actually something that you could do on your own. It's a pretty interesting thing to see happen, where eventually the more times we flip that coin, we will have our results get closer and closer to 1/2. So if we had the time, we would do it in class, and I have done it in the face-to-face class. It's a pretty interesting phenomenon, and it's not the only one. You don't have to do with flipping a fair coin. Really, any experiment that has equally likely chance, rolling a 6-sided die, for example, is the same thing, and counting the number of times a particular number comes up, that should approach 1/6, since each of the digits has a probability of 1/6 of occurring. All right, what we need to do to help you with your online homework is to determine whether each of the probabilities here is subjective, experimental, or classical. So part A says the probability of selecting a queen of spades out of a well-shuffled deck of cards is 4 out of 52. So in this case, no one is saying that they believe or feel or think that that is the probability, so it can't be the subjective in this case. Are we doing this over and over again and keeping track of the number of times a queen is selected? So is that happening here? The answer is no. So it definitely is not experimental. So it should be classical probability, right? That is the probability that we select the queen of spades. We have an economist predicting a 20% chance that technology stocks will decrease in value over the next year. Well, the economist is predicting this. That sounds subjective to me, right? It's their opinion. Now, you might say, well, what are they basing their opinion on? That requires some investigation. But in this case, it is subjective. It's their thought, their feeling, their prediction. We have a police officer who's looking at probabilities that a driver chosen at random will be driving under the influence of alcohol on a Friday night. So at a roadblock, he records the number of drivers stopped and the number of drivers with a blood alcohol level that's over the legal limit, and he determines that the probability is 3%, or 3 out of every 100 drivers. So this, because he is sort of repeating this over and over again for each individual that he stops, this would be a experimental or empirical probability, okay, because it's number of trials. It's a repeated sort of process each time a driver comes by. All right, we have some examples to work, get us used to a little bit of probability here. So we've got a dinner party, and Beck has some cheesecake options. Okay, so we've got 10 slices of chocolate, 12 caramel, 12 peanut butter chocolate, and 8 slices of strawberry. And the desserts are served to guests at random. Okay, some people wonder, why are we using randomization? And that is to make sure that there's no bias in the experiment. So part A wants to know, what is the probability that Beck's cheesecake contains peanuts? Okay, so first thing we have to figure out is how many options have peanuts, okay? And then the second thing we have to figure out is how many total options are there? In other words, how many cheesecakes are sitting on that dessert table? And this is actually a classical probability because it's going to be the number of outcomes in the event, which is the number that have peanuts, over the total number in sample space, okay? So let's see, N of E in this case would be 12. So how many options have peanut butter? I only see 12. Yep, peanut butter chocolate. Okay. And how many total should be 42? So if we add up 12, 12, 8, and 10, come up to 42. So the probability here is 12 out of 42, 2/7, and you have the decimal representation. So again, pick which representation you wish to use. All right, same situation. Part B this time is, what's the probability that Beck's dessert does not contain chocolate? Okay, so how many options don't contain chocolate? How many total options do we have? And again, still dealing with a classical probability. So how many do not contain chocolate? That would be 20. So that would be the caramel and strawberry, 8 plus 12. Okay, still 42 options. And so 20 out of 42 here, or 10/21 is our probability. All right, we have a beginning archer who managed to hit the target 50% of the time. And we want to know, what is the probability that in 3 shots, the archer will hit the target all 3 times? Now, we could, if we wanted to, use a tree diagram to find the probability of HHH, where H here is equal to a hit, or we could certainly use our notation. What is the probability of hit, 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 3 consecutive hits? We can also do this directly, and I think the directly makes a little bit more sense, hopefully to most people. And if we think about this logically, what happens on the first hit? Well, when we walk up to that target, we already have a 1/2 chance, right, of hitting the target, okay? What happens on the second? Well, there was also going to be the same chance, right? It's not going to decrease or increase. That is the probability on the second hit, and the same on the third. Now, we'll talk about this in a little while, but this is what we call a multi-stage experiment. We're doing this one after another. So it's, what's the probability we get a hit and a hit and a hit? So we need to multiply here. So this should come out to 1/8 or 0.125. So on 3 particular shots, this is what the probability should be. Now, someone might ask, well, what happens if we wanted 5 shots? Well, then we would multiply by 1/2 and multiply by 1/2 again. So that would be 1 out of 32. You'd keep multiplying each time. All right, next we have a family with 6 boys, and what we want to know is, what's the probability that the 7th child will also be a boy? This one is often confusing for people, okay? It's actually very, very straightforward. The only thing I'm interested in is the probability of the 7th child. Now that should say boy, not by, okay? So only 2 options here, a boy or a girl on this 7th child. So what happened previously has absolutely no bearing on what happens next. So in other words, what's the next child? So there is this illusion or fallacy that we tend to fall into with regards to probability, and that we seem to think that probability has a memory. Okay, not the case here. So the fact that the family has had 6 boys in a row, no problem. That has no bearing or impact on the probability that the 7th child will also be a boy. So it still remains 1/2, right? Probability does not have a memory. So in this case, each of the births of the children would be considered a independent event. And we'll talk about independent events in a bit. All right, so that is section 4.1. We are ready now to move into section 4.2, which deals with the complement and addition rules for probability. So people wonder, when do we add probabilities? That's what this section will be detailing. So after completing this section, you should be able to recall and apply several basic rules of probability. You should be able to define and find the complement of an event, look at mutually exclusive events, and given some scenarios, determine whether or not the events are mutually exclusive or not, and apply the correct addition formula. All right, so we have some important rules for probability. There are 3 on the screen that you may read, but there's one I want to emphasize, and that is the first one. The first one here is very, very important. Many of you will forget about this rule in probability, and here's what it says. It says for any event E, the probability that that event E occurs has to be between 0 and 1 inclusive. Inclusive means it could be equal to 0, it could be equal to 1. So what this is saying is that probabilities have to be a number in between 0 and 1, and they are allowed to be 0 and 1, okay? If somebody says to you that there is a 0% chance that it will rain, that means it guaranteed it will not rain. Probability of 0 means it is not going to happen. If someone says probability of an event occurring is 1, this means it will happen, guaranteed, okay? So probability has to be between there. So if you are doing computations to figure out probabilities, and you end up getting something that is negative or greater than 1, you made a mistake, okay? Something is wrong with the computation. So do keep this rule in mind. All right, now we have something called a complement of an event E, which is denoted as e to the power c. That's the notation that we use. Sometimes different textbooks might use e and have a bar on the top of it. So depends on the text, okay? This is the set of all outcomes in the sample space that are not in E. So let's see if we can make some sense of this by describing the complement. So the first event here is choosing a red card out of a standard deck of cards. So what would be the complement of this? Well, if you remember how the deck of cards is organized, you either have red or black. So if I am choosing a red card and I want the complement, that means the stuff that's not red. That means selecting a black card out of the standard deck of cards. We have 31 students in a statistics class. 15 are out sick with the flu. So what is the complement? The complement would be the people who are not in the group being sick. So that would be the 16 in the stats class who are not out sick with the flu. And finally, in your area, 91% of phone customers use Sprint. So what is the complement here? Well, the complement would be those who are not using Sprint, right? They're not in this group. So that's the 9% in my area who are not Sprint customers. So hopefully complements make a little bit more sense. Now, we have a rule that can help us with figuring out probabilities using complements. And what the rule says is if we take the probability of an event E and we add the probability of its complement, we need to get 1. Okay, and that's an important relationship because Rule 5 gives us a variation on this formula. And what you can do is you can solve the formula for either the probability of E or the probability of E complement. And this is where it comes in handy. So for example, the probability of E would be equal to 1 minus the probability of E complement. And we could also have another variation, which would be the probability of E complement is equal to 1 minus the probability of E. So multiple ways of thinking about this. So sometimes it is easier to figure out the probability of the complement versus computing the probability directly. And that's what we're going to look at in a couple of examples here. Okay, so if we are worried that there's a 35% chance that you're going to fail the upcoming test, what's the probability that you will pass the test? Well, the probability of passing would be equal to 1 minus the probability of not passing. So not passing here means we fail. So that would be 1 minus 1.35, and that would be equal to 0.65. So that is an example of how we can use the complement here to figure out then the probability that that we will pass. We have a 5% chance that none of the items on a scratch-off lottery ticket will be a winner. So we want to know what is the probability that at least one of the scratch-off items will win, okay? So this one is a bit tricky. That wording at least means one winner, two winners, etc. So how do we know then what the probability of having at least one winner is. Well, that is the same as 1 minus the probability that we don't have a winner. So we know the probability that we don't have a winner. That's 0.05. So 1 minus 0.05 is 0.95. So what is the probability that we will have at least one winner is a 0.95 chance, or 95% chance. Tell me where that lottery ticket is being sold. Anyway, okay, let's roll a pair of a standard six-sided die. And what we want to know is, what is the probability that neither die is a 3? Okay, so let's make sure we understand this. So we roll the 2 die, and we just look at the numbers. So for example, 2, 4 would be one of the outcomes in that sample space. One die is a 2, the other is a 4. What we want are the case where none of the die are 3s. Okay, so none of them. So 2, 4 would count towards this. Okay, so something like 3, 1 or 2, 3 would not count. That's something we don't want to put in the sample space. So interesting. So I would have to figure out then all the outcomes that don't have 3s. I might be here a minute. It's not impossible. You could use the chart method, the chart, to write down the pairs like we did with the sums, okay, and figure that out. So not so bad, but there is a little bit of a faster way, and that is using the complement. So what we need to do in order to use the complement is to figure out the outcomes that actually have at least one 3. And that is the complement that neither die is a 3. And if you don't believe me, go back and look at the example about the lottery tickets with at least and neither. It's the same idea. Okay, so I listed for us all the outcomes in which there is a 3. Okay, now you're going to notice that 3, 3 is only listed once. Okay, the order in which those things occur for 3, 3, it only counts as a single outcome. I know it's a bit strange, but we don't list it as a second outcome, okay, in that respect. So we have a total of 11. Okay, and we know that in this particular event, we have 36 total pairs, and that should be obvious because die has 6 sides. We have 2 of them. 6 times 6 is the 36. So this means that the probability that at least one of the die is a 3 is 11 out of 36. So using the complement, we take 1 minus 11 out of 36, and we get 25 out of 36. So that would be the probability here that neither die is a 3. Now, if you were doing this directly, you would have to figure out that there are 25 outcomes that do not have a 3. And again, it is not impossible. It would require you to have to use either the chart method or listing the outcomes out sort of in some sort of exhaustive list. Okay. And if we had more sides to the die, that might actually be a little bit harder to do. All right, now we're ready to get into when do we add probabilities. And so this is the rule that we have, rule 6, and it says for 2 events, E and F, the probability of E or F occurring is given by this formula. So first of all, we have some symbols here. This means union, and we interpret that to mean or. So I would read this as the probability of E union F, or alternatively, the probability of E or F. And this symbol here means intersection, and we interpret this to mean and. So the probability of E and F, or the probability of E intersect F, this means what the 2 outcomes have in common. What do they share? So we'll see if we can make some sense of this. So the big takeaway here is that you add probabilities when you see the word or. So you need to make sure that you're paying attention. So let's see if we can figure this out. All right, so we have Sarisa looking for a new condo to rent, and we have a realtor who has provided the following list of amenities for 17 available properties, and the list contains the following, okay? And the realtor selects the first condo they visit at random, and we want to know what is the probability that the property is either close to the subway or has low maintenance fee. So first of all, there's the word either, there's the word or. So hopefully you're seeing that. So we're looking here for the probability we're close to the subway or low maintenance fee. What I like to do with these is write them in words using the formula. So this means the probability that we have a subway probability of low maintenance fee plus the probability of low maintenance fee minus the probability of subway and low maintenance fee. So if we look carefully here, the number of properties that we have close to the subway are 6. That's right in the listing. Low maintenance fee is 7. And you'll notice that we do have 2 properties that are close to the subway and have low maintenance fee. So that's the intersection that we have to remove, right? We have properties that have that in common. So that gives us 11 out of the 20, or 0.55. Now, one of the things you're going to notice here is, why am I giving a denominator of 20, okay, when it said that there are 17 available properties, and if you count the number of properties in the list, you actually get 23. So why is there a discrepancy? First of all, 17 should be 20, so that's my fault for not changing that, okay? That's what I get for not reading this carefully, so there should be 20. And if you look at the list, there are 23. And people say, well, why are there 23? Well, that's because we have 3 properties that got double counted. And that's the ones that are listed twice: close to the subway and low maintenance fee, and green space and newly renovated. So you have to remove those. They've already been counted. So that's why we're looking here at only 20. Now, this example will make it a little bit more clear as to why we are only dealing with having to subtract some quantity. This will make it a bit more clear. So we have a U.S. Senate. It's voting on a health care bill. And we have a chart here that shows the political affiliation, okay, and what they voted, the number who voted for or against the bill. And a lobbyist is looking to stop a senator after the vote, and we want to know the probability that the senator will either be Republican or have voted against the bill. So there's the key word there, or. Okay, so Republican or voted against the bill. So again, writing this out in words so I can see it: probability of a Republican plus probability of voted against the bill minus the probability that somebody is Republican and voted against the bill. Okay, so first of all, I need to figure out how many Republicans there are who are present here, and that would be 50. So that's the 43 plus 7. Okay. There it is, 50 out of the 100. Hopefully everybody remembers 100 senators, U.S. senators. Go back to your political science class, okay? 2 representing each state. Now the question is, how many voted against the bill? How many people did? Okay, well, that's the sum of 21, 7, and 4, so that would be 32 out of the 100. And I want you to notice something. We circled a number on here twice, didn't we? Okay, that number happens to represent the number of Republicans who voted against the bill. So that's the extra number we have to remove. We counted it twice. Okay, so we're taking that 7 out. And we end up with 75 out of the 100 senators, or 0.75. Okay. All right, next we roll a pair of dice, 6-sided dice, we can assume. We want to know, what is the probability of rolling either a total less than 4, okay, or a total that's equal to 10. All right, so there's or, I see or, but I need to understand this. A total less than 4, okay, a total equal to 10. All right, so there it is in words: some less than 4, some equal to 10. So writing this out using our formula. Okay, so here is our sample space. If you recall, I said we were going to be using this again from section 4.1. So there it is. All right, so I need to know, where are the sums less than 4? I hope it's obvious there are 3 of them. It's 3, 3, and 2. Those are the only sums. They're in this corner here. If I can get the mouse working, there it is. Okay, just right here. All right. And then I need to know how many sums are equal to 10. Well, that's on this diagonal down here. Okay, so just 3. Now the question is it possible to have a sum less than 4 and equal to 10? Can I have both things occur at once? And the answer is no. I cannot have a sum that is both less than 4 and equal to 10, because if I'm equal to 10, I'm not less than 4. And if I'm less than 4, I'm not equal to 10. So that is impossible. That's why that probability is 0. So the answer here is simply 1/6. Now, what this example demonstrates is something rather interesting, and this is what happens when we have an intersection between 2 events that is empty, okay? And this has a meaning, so this is leading us on to something, okay? So let's see what this is actually telling us. Well, what it's telling us is that those 2 events, getting a sum less than 4 and equal to 10, are mutually exclusive, and that's because there's nothing in common. So put another way, the intersection is the empty set, nothing in common. So rule 7 says if you have two events that are mutually exclusive, then what you simply do is add the probabilities. There's no worry, no need to have to subtract anything because that intersection is empty. So if you come across mutually exclusive events, you won't have to worry about subtracting what they have in common because it's just going to be 0. So let's see if we can make some sense of this. All right, so Caleb is purchasing a brand new car, and his friends have some debate on the type of model that he's going to choose. And so these are the probabilities for each of the 4 models, or makes rather. And the question that we're being asked here is that Devin is betting that Caleb will choose either the Toyota or the Jeep. Okay, Toyota or the Jeep. So there it is. Now the question is, can he select a Toyota and a Jeep? In other words, a single car that is both. Okay, so we're not saying he's going to purchase 2 vehicles. No. It's either the Toyota or the Jeep. So that intersection, can we purchase a vehicle that is simultaneously both a Toyota and Jeep? The answer is no. So that's why these are mutually exclusive, and we simply add the 2 probabilities. Okay, we have an exit on the interstate, and we are looking for the probability here that this driver is going to refuel at a Shell, Exxon, or Chevron gas station. So we have 3 possibilities here. So each of these are mutually exclusive. I cannot stop at a gas station that is simultaneously Shell, Exxon, and Chevron, right? They're all separate, mutually exclusive. So we simply capture the probabilities from the chart, sum them, and we get our result. And you'll notice that I'm leaving these as the decimal. I'm not converting them to a percentage or fraction. If it's presented as a decimal, sometimes it's just easier to leave it that way. All right, so a quick recap on section 4.2. So do make sure you remember rule number 1, that probabilities have to be between 0 and 1 inclusive. If you do get an answer that's negative or greater than 1, it means you made a mistake. Double check your work. Make sure you use the complement, okay, as it might make things a bit easier for you. The complement of neither is at least, and that also works vice versa, guys. The complement of at least is neither, so that might come in handy for you. Keep an eye out for that key word. Speaking of keywords, if we see the word or, this means we need to add probabilities, okay? And do make sure you check the events to make sure that things are mutually exclusive or not, since that does make a difference in the formula that you're going to be using, okay? All right, we are ready to move into section 4.3, which deals with multiplying probabilities. And before we get to that, we need to look at independent and dependent events. So after completing this section, you should be able to figure out or understand and determine whether or not events are independent or dependent. You should be able to apply the correct multiplication rule for computing these probabilities with independent and dependent events. You should also be able to determine when to use conditional probability formulas and carry out its computation. And finally, apply the fundamental counting principle. Let's see if we can make some sense of this. So independent and dependent events. Now, when we deal with multiplication, we generally consider multi-stage experiments, and this is generally when we're doing more than one thing. If you remember to the example in section 4.1 with the archer, right? The archer was shooting a target 3 times in a row. That's considered a multi-stage experiment. If you remember writing the sample space for a coin toss and rolling a 6-sided die, that's considered a multi-stage experiment. We're doing more than one thing, okay? So that's what we mean by multi-stage. So again, flipping a coin, rolling a die. Many of the examples that we've looked at, especially in 4.2, only dealt with what we call a single stage experiment, just doing one thing. What's the probability that I select a senator who is Republican or voted against the bill? So I'm selecting one individual thing. So it's important we read carefully. Now, 2 events are said to be independent if one event does not influence the probability of the other event. And the wording that I'm using here is with replacement. So in other words, I do something and I put the thing or the object back. Okay, so in other words, I select a card, I look at it, and I put it back into the deck with replacement. I haven't changed anything about the object that I am experimenting with. That's what we mean by independent, okay? For two independents, E and F, the probability that E and F occurs, or the intersection, is equal to the product of the two events. Okay, so let's see if we can make some sense of what this means. And again, I want to emphasize that independent events is with that phrase, with replacement. Okay, so don't forget with replacement. There's our arrow there. Very, very important phrase. Okay, so we want to find the probability of choosing two cards, okay, a king and a queen from a standard deck of cards with replacement. And so the question is, are choosing these two, are these two events, choosing each card, independent? And the answer is yes, because I select the king and I put the king back into the deck. That's the idea behind with replacement. And so here we're looking at the probability of selecting a king and a queen. So very easy. How many kings are in the deck? 4 out of 52. How many queens? 4 out of 52. So this probability is 1 out of 169. I'm not changing anything about selecting the queen. It's with replacement. So selecting the queen has no bearing on what happened before. And I could have selected 50 cards. It has no bearing with this idea of with replacement. Okay, that's the important thing here. All right, we have a table of infractions, and probabilities that these infractions will occur are listed. We want to know what's the probability of being late, taking an unauthorized break, and leaving early. Okay, so putting all of these together means we need to multiply the probabilities of each one of these infractions. These would be independent. One will not have a bearing on the other necessarily. Okay, I won't ask anybody who's guilty of any of these things, but we would treat these as being independent events unless told otherwise. Okay, so in this case, we simply multiply the three probabilities and we get our solution. Some people might argue that maybe somebody being tardy is a form of insubordination if they're told to be there on time and they get warnings, etc. We're not getting into the muddy details on these things. So in this instance, we treat these as independent occurrences. Now, we do have something called a dependent event. This is where the occurrence of one event will impact or affect the probability of the other event. And the phrase we use here is without replacement. That's the key wording here. So we have a probability formula for this, which says for two dependent events, E and F, the probability of E and F occurring is given by the following formula. Now you'll notice that there's a strange symbol in the second factor, okay? And that symbol that's really a vertical line has a meaning of given, okay? And it's used in conditional probability. So in this instance, we are saying that the second probability is dependent on what happened first, namely the probability of E. So how we read this is the probability of F given E. That's how that's read. Probability of F given E. So that means that E has happened already, and now I am going to figure out the probability of F, but I have to remember E has occurred. Something is impacting then, that event E is impacting my computation and consideration for the probability of F. I need to keep that in mind. There's some sort of impact. So that second occurrence, we have to think a bit carefully. And again, that phrase with replacement, without replacement rather, is important. We have to think very carefully. So with replacement, very easy. Independent. Without replacement means dependent. So we have to think carefully. So let's return to that example about the king and the queen, but this time we're doing it without replacement. So I select the king and I throw it on the ground. Okay, so now what has happened to the deck of cards? Okay, you might be saying, well, there's one less card in it. We'll get to that in a minute. So the probability that in this instance of selecting a king and the queen becomes the probability of selecting the king times the probability of selecting a queen given we have selected a king already. So the queen is the second draw. The king was the first. So I'm reminding myself here that the queen, the selection of the queen, depends on the first card being a king. So we have to be careful. We have to consider what has happened to the deck. So first of all, there are 4 kings in the deck out of 52 cards. Wonderful. Now, if you listened carefully, what I said is we selected the king and I threw it on the ground. What has now happened? Well, there are still 4 queens in the deck, but now the problem is there's one less card in the deck. We went from 52 down to 51. So the denominator has to be 51. That's the idea then behind dependence. So now the occurrence of that second card being selected, there's a change, okay? And it has an impact then on the probability. Now, some people might be wondering, what happens if we selected a king, a second king? Well, if there were 4 in the deck and I threw that on the ground and wanted to select a second king, now it went from 4 down to 3 with still 51 cards in the deck. So there are some implications if we're selecting the same value, okay, for the deck of cards. So again, 51 because we are doing this without replacement. So very, very important we remember these details, okay, without replacement. So make sure you're thinking carefully. Okay, we want to find the probability that the second card drawn is red, given the first card was a diamond. Now, this one is interesting, okay? This one is different than the last example. The last example, I hope you read carefully, we were selecting 2 cards, right? A king and a queen. Look what this one says. Find the probability that the second card drawn is red, given the first card was a diamond. All I want is 1 card. In fact, the first sentence that I skipped over says that 1 card is drawn from a standard deck of cards without replacement. All I want to know is what's the probability that I select a red card, but we drew 1 card already, and that was a diamond. Okay, so what then is the probability? So we're only considering the red card, not 2 cards in a row, just 1, based on something that had already happened. Okay, so the probability that I select a red card, given the first card was a diamond, is 25 out of 51. Now let's make sure we understand why that is the case. We have to remember that there's 1 less card in the deck, okay, because the diamond got thrown on the ground, so we went from 52 to 51. But we also have to remember that a diamond is red. So there are 26 red cards in the deck, and if I've already removed it, there's also 1 less red card. Okay, so that's why there are 25 here. So very tricky. So make sure, again, you're reading carefully. What am I exactly selecting? Let's find the probability that we select 2 face cards in a row without replacement. So face cards we have to remember are the jacks, queens, and the kings, and there are 4 each, so 12 total. And they're called face cards because they have a face. All right, easy enough. Without replacement means dependent events. So we want the probability we select a face card and a face card. Because it's dependent events, the second face card is going to depend on the first card being a face card, okay? So I hope we agree that the first face card, there are 12 out of 52. And the second face card, well, since we've already looked at a face card, there has to be 1 less of them. So that's 11, and there's 1 less card in the deck, which is 50. So in this case, 11 out of 221. We have 17 men and 24 women in a Rotary Club. We want to find the probability that a man is chosen first and then a female is chosen second, okay? Now it says, notice the problem does not say without replacement, so we need to exercise some common sense. So if we are selecting these individuals, let's say for an event or a raffle, it doesn't make sense that they would go back into the pool of people to select. So we can assume here that this would be dependent without replacement. So the probability that we select a male times the probability we select a female, given the first person selected was a male. So we have 17 males in the Rotary Club, 41 total people. The second draw would be 24, since that's the number of women, but this time the denominator would be 40, 1 less individual in the pool of people to select. So if since the genders are different, that's why the denominator has not changed. It's 24 for the women. There's not 1 less female because the first person chosen was a male. Had the first person been chosen been a female or a woman, then what we have had would be, instead of 17 on the first fraction, would have been 24, and on the second fraction, 23. Okay, just like when we were looking at the face card. So it is important to make sure that we distinguish which groups we are selecting from. Now, the other part to this section deals with what we call conditional probability, and this can be a bit tricky. You may recall for a moment rule number 9, which dealt with the probabilities that involved dependent events, okay? And if we solve this particular formula for the conditional portion of the probability, what we end up with then is the following fraction. It's the probability of intersection with F, divided by the probability of E. And so this leads us to then rule number 10, which tells us what the probability of F is given event E, okay? So let's see if we can make some sense of this. So we have 300 applicants in a pool for a job. 212 are female, 110 are female and have a graduate degree. We want to find the probability that someone chosen from the pool has a graduate degree, given they are female. So what you'll notice is I wrote this as the probability that somebody has a graduate degree, given they're female. F is what stands for female. Applying the formula, we have the numerator of the graduate degree and female, and in the denominator, the probability that they are female. So in the numerator, we were told that there are 110 females who have a graduate degree out of the 300, and we have 212 females. So that's why we have 212 over 300. That simplifies to 110 over 212, or 55 over 106. Now, part B is asking us to figure out the following. If we have 152 applicants with a graduate degree, we want to find the probability that a female is chosen given an applicant has a graduate degree. Okay, so this is sort of the reverse, flipping the variables. People might wonder what happens with this. Well, the numerator remains unchanged. Okay, so we have the probability of a graduate degree and female. So those two switch, still 110 out of 300. But this time the denominator becomes the probability that somebody has a graduate degree. That's not what the last slide had. The last slide was the probability of female in the denominator. If you don't believe me, rewind the video. So this changes to 152 out of 300, and our probability then is 55 over 76. And what you should notice is that the probabilities here are different. So it is not correct to assume that the probability of F given E is the same as the probability of E given F. That is not correct to say that they are equal. So the order in which we write these events for conditional probability does in fact matter. So we have to take and exercise some care with this. This section concludes with what's known as the fundamental counting principle. And this is kind of interesting. What it says is we consider multi-stage experiments with different stages, okay, n different stages. And the first stage has a certain number of outcomes. We can call it K1. The second stage has K2 outcomes, etc. So the total number of outcomes would be us multiplying K1 times K2 times K3 times however many stages there are. Okay, so it basically says is we're doing a bunch of multiplying here. So let's see if we can understand this. Luke has to take 4 classes, and he has the ability to choose from 8 English, 12 algebra, 11 history, and 5 physics. So each of these represents a stage. So English is a stage, algebra, history, physics are all each stages. If one course from each category is selected, how many possible schedule options exist? Okay, so since we have 4 stages here, I should say FOUR, each class being represented as a stage, we have the total options. Well, how many different outcomes do we have for each? Well, English has 8, algebra has 12, history has 11, physics has 5. So that's a grand total of 5,280 different schedule options that can be created. Now we have some other applications to this. Let's consider access IDs, okay, here at Wayne State University. So if anyone from the general public is watching this, the access ID is a identifier that's often used for email purposes. Everybody has one. It is 2 letters, 2 lowercase letters, followed by 4 numbers, digits, 0 to 9. So for example, AA 1234 would be considered an access ID. AA 0000 could be considered an access ID. So 2 letters followed by 4 numbers, and the numbers used are the digits 0 to 9. So how many possible axis IDs are there? Well, since the letters, there are 26 of them, that's 26 times 26, and we have the digits 0 to 9, that represents 10 digits. For each of the 4 positions, that's 10 times 10 times 10 times 10, or about 6.7 million different axis IDs that are possible at Wayne State University. Now, somebody might wonder, well, what happens when we get to that many students over the time? Well, it's easy. They just add another digit onto the end, or maybe add another letter, so everybody has 3 letters. Okay, how many axis IDs are possible if no letter may repeat? Okay, so repeats are not allowed. Well, the numbers aren't going to change, so that's going to remain as 10 to the 4th power, or 10 times 10 times 10 times 10. But since we can't have repeating letters, that's going to be 26 times 25, right? So if I selected, let's say, B for the first letter, the second pool of the second letter, the number of choices I have, the pool of letters decreases by 1 because I can't use B again. So there would be 25 of them. Okay, so that would be 6.5 million. Similar, what happens if no letter may repeat? Okay, so excuse me, no number can repeat. So letters can repeat, so that would remain 26 times 26. But what about the numbers? Well, the first number we would have a possibility of 10 choices. Okay, let's say I picked 4. The second number could not be 4, so there would be 1 less. There would be 9, and the third, there would be another 1 less. That would be 8, and 7, etc. So each of those digits the pool of digits available would decrease. Okay, so in this instance, about 3.4 million axis IDs. What happens, how many axis ID are possible if we have the first 2 letters being the same? So we have to remember, what does it mean to be the same? So something like AA, BB, CC, DD, EE, etc. So how many possibilities are there for letters to repeat? I hope it makes sense that there are only 26. There are only 26 letters in the alphabet. Okay, so there are only 26 pairs that are exactly the same. A, B, B, C, C. Okay, keep counting them all if you need to. List them if you need to. There are only 26. So in this instance, there would only be 260,000 possible axis IDs where the first 2 letters are the same. So anybody who has the first 2 letters are the same, you're in a rare group. Okay, 260,000 out of 6.7 million. Not bad. And we want to know, what is the probability of selecting an axis ID where no letter repeats? So here we're mixing some probability with counting, okay? So what we need to do is figure out what the total number of axis IDs are with no letter repeating. That's easy. That's the second example. That's 6.5 million. The total number of axis IDs, that was the first one we did, 6.7 million. So that gives us 25 out of 26. So pretty good probability, 96.15% chance that you've got an axis ID out there with no letter repeating. I'm in that group. My first 2 letters are AO. All right, section 4.4, the last one that we're going to deal with is looking at counting with permutations and combinations as we wrap up this chapter 4. So after completing this section, you should be able to simplify expressions that involve factorials. We should be able to distinguish when to use a permutation or combination formula, and certainly being able to carry out the calculations involving these formulas. So first of all, what is a factorial? So factorial is given by n, and yes, you're reading that correctly. It's an exclamation point. So please don't read this with excitement. So it's not n, okay? It's n factorial. That's how we read it, okay? It's a bit strange, I know. What it says we do is we take each factor, okay, so whatever n is a number, and we write a string of factors. So it's a string of multiplication factors that we're doing, and each factor is 1 less than the one before it. Okay, so we'll look at an example here in a moment. First, please note that 0 factorial is equal to 1. You may see 0 factorial pop up. It is not equal to 0. It is equal to 1. So we accept that as a fact. So let's compute the following. What is 7 factorial? By the definition, what the definition says that we have to do is you take 7 as the first factor, then we take n minus 1. N is 7, so 7 minus 1 times 7 minus 2 times 7 minus 3 times 7 minus 4, etc. That simplifies to the following expression: 7 times 6 times 5 times 4 times 3 times 2 minus 1. So you notice that each factor is 1 less than the one before it, and we finish with 1. Okay, so 100 factorial would be 100 times 99 times 98, etc., all the way down to 2 times 1. 3 million factorial, you get the idea. Okay, so this answer is 5,040. Now we do things with expressions. So what happens if you have something like 4 factorial over 0 factorial? First thing is don't panic, because I told you 0 factorial was equal to 1. 4 factorial is simple enough. 4 times 3 times 2 times 1, or 24. Now, how about something like 95 factorial over 93 factorial? Well, I hope we understand that 95 factorial will be this long list of factors down to 2 times 1. Same thing for 93. Now, I'm not expecting anybody to sit here and try to compute all of this out. There's some things you should notice. I hope you all see that the 93 over 92, 93 over 93, 92 over 92, 91 over 91, etc., even 2 over 1, 2 over 2, 1 over 1, all of those go away. That's what those lines are indicating. Those are all 1 over 1s, right? They're all simplify out. So what you're really left with is 95 times 94. So that very complicated expression simplifies to something so nice as 95 times 94, or 8,930. Okay, so that's all we are left with. Okay, let's look at 5 factorial over 5 minus 3 factorial. Okay, so first of all, you have to do some order of operations. So we have to do 5 minus 3 first. So that's how we get 2 factorial in the denominator. We expand these expressions, 5 factorial and 2 factorial. What you should notice again is that the 2 over 2, 1 over 1, okay, go away. All we're left with is 5 times 4 times 3, or 60. And similarly, 6 minus 2 is 4, so we have 6 factorial over 2 factorial over 4 factorial. And what you should notice here is that the 4 over 4, 3 over 3, 2 over 2, 1 over 1 all go away. And what we're left with then is 6 times 5, or 30 over 2, okay, or 15. So all of that stuff, there it is there, a little bit late on the animation, but that's okay. All of these terms go away. Okay, so it makes it nice and easy. You might be wondering, why am I presenting these strange expressions? And that's because you're going to see them explicitly listed in the permutations and combinations that we're looking at here. So when do we use each? So permutations are used when the order or arrangements of objects matters. So this means things like ranking, positions, titles, placement, etc., where we care about the order. And you'll notice the formula, okay, NPR. N here stands for the total number of objects that we have. R is the number of objects that I want to arrange. So for example, if I have, let's say 30 people, okay, that would be N. And I want to arrange 6 of them in specific titles. Okay, so the R here would be 6. So 30 is the number, the pool of people I have. R is how many I'm looking to arrange. Similarly, combination formula, okay, very similar to permutation, but this is used when the order does not matter. Okay, we don't care what the order is. So this is where there's no concern for rank, position, titles, placement, etc. So again, if I have a group of 30 people, and I want to take 6 of them and build a group, and I don't care the arrangement, okay, N would remain as 30, R would be 6. And so you'll notice there's an extra factor of R factorial in the denominator as compared to the permutation formula. So let's see if we can put this to use. We have a class of 18 fifth graders. They're holding elections for president, vice president, and secretary. We want to know in how many ways can officers be selected. So these are dealing with positions. So who holds these positions matter. If you don't believe me, think about the president, the vice president, and the secretary of an organization you are part of. Okay, it does matter who is in these leadership positions. They have different agendas, organizational styles, management, etc. So we're dealing with a permutation here. So in this case, the pool of individuals we're selecting from is 18, and the number we need is 3, because there are only 3 positions, president, VP, and secretary. If they added treasurer, then that would change to 4. So 18 factorial, divided by 18 minus 3 factorial. So that's 18 factorial over 15 factorial. Using the simplification we did before, this would be 18 times 17 times 16, or 4,896. Because people are going to be asking, what kind of work do I need to show for the purposes of the homework or the test? What you see on the screen is what I would be expecting on homework, test, or the final. Next, we have a cafeteria that has 7 different dishes to choose from. We want 3 for a meal. In how many ways can the plate be organized? So the order in which the dishes are plated does not matter. So the fact that you get dessert first, followed by your salad, followed by the entree, is not going to be impactful if you had the entree first, followed by dessert, and then the salad. It doesn't matter how the plate gets organized, as long as you get all of your food. Okay. Now, some people might say, well, it does matter to me. Well, that's mattering to you. You have personal preference, and the purposes of this discussion, it does not matter how your plate is organized. So since we have 7 dishes to choose from and we only want 3, this would be 7C3, okay, which simplifies again to 35. And people are going to ask, what sort of work do we need to show? What you see in red is what I would be expecting for homework, exam, or the final exam. All right, we have a baseball batting order of 9 players that's randomly chosen. We want to know the probability that the order chosen for the second game is the same as the first game. So positions in a batting lineup, those matter. Okay, if we think about our Detroit Tigers, obviously this video is being based institution in Michigan, so we are Detroit fans here. So it does matter who is going to be the first batter, the second, the third, fourth, etc. So this deals with a permutation. So we have 9 players, and we need to arrange 9 players. So this one's a bit interesting. So I have 9 players, and I need to arrange all 9 in an order, and that order is going to matter. So our denominator here is going to be 0 factorial, okay? And that's fine. That's going to be 1. So it should make sense that this is going to be 9 factorial, 9 times 8 times 7 times 6 times 5, etc. Because if we have 9 players and I pick one for the first batting position, then how many players do I have for the second batting position to choose from? The answer is 8. Okay, I select that 8th one. How many for the third position? That would be 7. So it's going to decrease by 1 each time. Long story short, 362,880 potential lineups that we have here. So it's quite a bit of lineups if you think about it. All right. Next example here is Maya has 15 blocks in colors of red, blue, and yellow, and she pulls out 3 blocks, and we want to know what is the probability that the blocks are red, blue, and yellow. So this one combines probability and counting. And we want to know here, does the order matter? And that's an interesting question. Now, the outcome is pretty specific if you consider this, where it says RBY. They didn't just say, what's the probability that one of the blocks is red, one of the blocks is blue, and one of the blocks is yellow. This is pretty explicit that it's RBY. So I'm going to assume that this is a permutation because the order matters. Some of you out there might argue differently, and that's fine. But because I see it listed as RBY, I'm going to assume that this is a permutation. Otherwise, they would have said just a selection of a red, a blue, and a yellow. In this case, it is pretty explicit. So we need to know the total number of arrangements that we have first of all. So in this case, since the order matters, it's a permutation. We have 15 of these blocks. Again, we're only selecting 3. So that gives me 2,730 total arrangements of these blocks, not total blocks, but total arrangements of these blocks, okay? So the outcome RBY only happens once because it is a specific arrangement. So the probability here would be 1 out of that 2,730. So a pretty low chance. Now, as I'm thinking about this, I realized that in the first example with the batting order, I didn't answer the question. This is what's the probability that the order chosen for the second game is going to be the same as the first game. That would also be 1, right? There's only 1 batting order in the first game. And so that would be 1 out of the 362,880. So same idea as this second one here with the permutation. Now, with the idea with Maya, if we were looking at combination, that might be a little bit different. That's going to change then potentially the the probability, especially for the numerator, because in a permutation, we're counting each arrangement as one, right? So RBY is this very specific arrangement. If we're thinking about the combination of a red, a blue, and a yellow, that might force us to think about this a little bit differently. So I would encourage you then to try this example with Maya and the blocks from the combination perspective. If folks are thinking that this is interpreting the red, blue, and yellow from the perspective of a combination, where it doesn't matter the order in which he pulls out those three blocks. So there may be implication then on what your numerator may be. We'll have to see. All right, this video has been pretty long, so we have covered quite a bit of ground across 4 different sections, all the topics that are listed here. So glad you made it to the end of the video as we wrap up our discussion on probability.